Hello, everyone. So, I will warn you, I may look a little tired today, but that's just because I had a relatively productive night and my brain didn't want it to end, I guess. So I got to sleep around 5 in the morning, and I woke up at 10:30. So it's not the best night's sleep, but I got a little nap in. So today, you may see from the title, although it's a pun, so it's kind of hard to decipher, that I am going to be talking about a math topic of complex roots. This is not a. It's not a easy. It's not necessarily hard of a math topic, but it's not normal. It's not the normal scheme of math that most people have a grasp on. So I thought it'd be nice to at least touch upon the idea of it so that um, if it ever came up in everyday life, you would have a at least general understanding of it. And also another topic I wanted to talk about was something that I just randomly thought of yesterday, and I'll leave that um, till later so that I can get more into it. So today we have the ball drop program running down in the corner here, that way. So just like the last Saturday stream, we are waiting to see if the optimizer will kick in. So this requires that the stuck value get up to 5, and that it is possible that that will not happen even in this stream. So we will keep an eye on that, and if you see that happen, please let me know, or I'll hopefully see it happen. But that's just something that we want to keep an eye on because I want to make sure that it's working. I'm pretty sure that it's working because I tried it on the previous running, which was already stuck, but I want to see it kick in and see if it actually affects the learning process. So we will keep an eye on that. Um, but that's just what's happening with the ball drop program. Now, another reason that I was so productive last night was because I was developing the concepts for new updates to the environment project. So I just want to show you that here I have the notes, and it keeps going and it keeps going, and I have another page of notes right there, and then this is the end of those notes. So it was a lot. I had to just get out of my head and onto paper, but I plan to start working on those soon. But today's stream is not about the environment project. Today's stream is about the ball drop project, or the optimizer. So I want to save those ideas until Wednesday, but hopefully I will have done a little bit of work on that before Wednesday so that I will know what I'm getting into. So the current running of Jeffrey is still going strong. So just a quick update, I wanted to say some things that I noticed with Jeffrey. So I saw that something significant that is kind of it's minor, but it's also nice to see, and it's a nice change. Is that I saw that when Jeffrey was shooting his gun a lot and would run outside of the light, then he would get to an area where he would get to a point where the next shot would kill his battery, and he was actually stopping. So when his battery got low, he would not shoot the gun any longer, which allowed him to last longer. It allowed his battery life to last longer, and that's nice because it actually means that that's a decently intuitive decision. So that's a nice improvement that I've seen, but I think that even with the current changes, his learning is limited. So I have with my notes, with the ideas that I was working on last night, I do believe I have at least the next step and maybe the step after that for a new learning process for Jeffrey. So I will be talking more about that on Wednesday. But today I'm talking about I'm having a normal Saturday stream. So I'm just gonna play a quick ad and get into my first topic. So I will be right back. Okay, I believe we're back. So today, um, like I said, I will be talking about complex roots. So this is having to deal with roots of high power, and so that means over 2. Although this method of finding the answer still works for 2, it's just not significant. So now, if you've taken any minor algebra class, you know that when you take the square root of something, then you get then you know that let's just get an example. So let's say hold on, I have to get paint up. Let's say I took the square root of 2. So that's bad. Let's take a perfect square. So let's grab 9. So we have the square root of 9, and so if you know basic math, then you know that this is 3, but it is also -3. So a lot of people say plus or minus 3, and those are both of the answers. So if you are doing anything that needs to encompass all the answers, then this is what you do. If you're just trying to get one of the answers, +3 will suffice. But so in most cases, the positive answer is okay. But what the point that I want to get across with this idea is that there is a number of answers. So let's say there's n answers for every n power root you're taking. So n x. So there's n number of answers for every n power root you have. So what is interesting is that in normal classes, it is taught that if you take the cube root of something, so I'm going to clear this just for sanity's sake. So let's take the cube root of 27, because 27 is 3 cubed. So 27 cubed, or cube root. So what most people will say is that this is equal to strictly 3. And that is convenient for everyday purposes, but it is not the full picture. So what's happening here, and the reason that -3 is not included in this is because it is not actually an answer to this problem. If you cube -3, then you get -27, and that can be easily seen. So -3 times -3 is 9, but then 9 times -3, you only have one. It's a negative times a positive, so it becomes a negative. So what's going on here is that there are other answers to this problem that aren't being seen. And the reason that most people don't consider them in normal situations is because they are complex answers. So what I mean by complex is that they have imaginary numbers in them. So they fall under the category of a number in the format a plus bi, where a is the real component and b is the imaginary component. And so what happens with imaginary numbers is you can actually plot them on a graph, not a normal graph of x and y, but a graph of real numbers and imaginary numbers. I'm not sure if it's the actual terminology, but I'm just going to put the complex C here, just for just to have something labeling it. So like I was saying, you can graph a complex number. So the real component is a, so that's a, and the imaginary component is b. And so you get this point out in space that you can draw a line to, and what happens is you can find the so-called magnitude of this imaginary number, or this complex number. So the magnitude, if you know anything about vectors, is the length of this line. So it's the square root of a squared plus b squared. And so that will give you the answer to this. Well, that will give you the magnitude of this imaginary number. Now this will come back into play in a bit. So I just want to. So I've mentioned so now that each root of a higher power has that many answers. So in this case, there are 2 hidden answers, and so we need to find them. So I'm going to clear the board here. So what happens is that there are other complex numbers that when you multiply them by themselves 3 times, then you get 27. And so there's a nice method to finding those complex numbers that makes it fairly simple to locate them. So we'll draw our graph here, and we can just remember that the horizontal is the real axis. So first we start out with, we know that 3 is an answer, right? Because that's just what we've learned, that's our intuition. So we can put, I'm going to grab blue here, we can put a vector that is right along the real axis that goes to 3, because we know that that's one answer. Now, there are 2 other answers, and what is the interesting quality of how these answers are oriented is that they are equally spread apart in terms of if you draw a circle with radius 3, then they will be as far away from each other as possible. So since there's 3 answers, then we can take the total amount of radians in a circle, which is 2 pi, or 360 degrees for those who don't like radians, and you can divide that by 3, and that gives you, well, that's the answer. So you can't simplify that anymore, but that's 120 degrees. So what that means is if we draw another line 120 degrees away from this this first vector, and then draw another vector 120 degrees from that, and then we have 120 degrees left. So in total, it does the full 360, the full 2 pi. Then we can find what these other points are. And so you can see, because these have vertical components to them, they actually are complex numbers instead of real numbers. So since we said that this is 120 degrees right here, then we know that this in turn is 60 degrees because it's making a full line. So if we take the we can do this by sine and cosine. So then the sine of 60 degrees is let me write this out. So the sine of 60 degrees is root 3 over 2. And the cosine of 60 degrees, so I'm trying to not have you guys sitting here while I'm writing stuff out. The cosine of 60 degrees is equal to 1/2. So what we have is that we have 3 times this cosine, the cosine part, which is 1/2, plus the sine part, which is root 3 over 2, times our imaginary component. And that is the answer. So we can multiply this out. It won't really change much. We'll just get 3/2 plus 3 root 3 over 2 times I. And that is our complex number that if we multiply by itself 3 times, we will get 27. So this is also, so the reciprocal of this number, which is just changing the plus sign to a negative, will also be a complex number just based off the symmetry of this orientation here. So it will also be a complex root of 27. So this can be done for any root. So it doesn't just work for our cube root. If we take a fourth root, then we have a circle with our origin in the middle. And if you know anything about fourth roots, then in most situations you would consider them just like square roots, other than the fact that obviously you take the fourth root of it, but there is a positive and a negative answer to them. And this makes sense in our idea. So we have the original root, which is right here, and then if we take 2 pi and divide it by 4, then we get pi over 2, which is 90 degrees. So we change the angle 90 degrees, and then 90 degrees, and then 90 degrees. And what happens is that the two real answers that we get are positive and negative. And this will happen for any even root, or any even, any even root. So since we're taking the fourth root, this happens because then it is a, because it requires, so 360 can be divided by 2, which is 180. So then when you take the 2 out of the even root and the 2 out of the 360, then it ends up giving you 180 at some point. So Um, but then all the odd numbers will miss this miss this negative side of it. So the odd numbers are specific to what their starting sign was. Um, so this is an interesting quality, and that's why we see that the positive and negative numbers play different roles. So then also we can see that for the square root, if you take the square root of a negative number, then actually we have stuck of 5, so we should be seeing the optimizer kick in here. So if you take the square root of a negative number, then you get two answers that are imaginary. But if you took the fourth root of a negative number, then it would get a little more complex. So that's basically what I wanted to point out. There's also this idea with graphing these imaginary numbers of the Euler equation, which is nice just to know. I'm not really going to get into it too much, but I wanted to write it out for you guys. So the Euler equation is e to the I theta is equal to cosine theta plus I sine theta. And the reason that this is interesting is that you can actually, is that e to an imaginary power is actually a sinusoidal graph, and what ends up happening is because it's in this imaginary plane, it is a circle. So what happens is e to the I theta is just a circle of radius, whatever the coefficient is here. And so originally it's a circle of radius 1. And so a interesting idea is that e to the I pi, so that's a rational number to an imaginary rational number power is equal to -1. And this makes sense because if we have pi as the angle, then our cosine will be 1. It will be -1, and our sine will be 0. There'll be no imaginary component. So the angle here will just be 180, which is pi. So that's just something I wanted to point out. That's if you ever don't know the answer to something, this is probably the answer, just because it's so awesome. But I don't have too much more to talk about on this topic. I don't want to bore people with my droning on, trying to squeeze more information out of this when I am not the most versed on the mathematical community. So I will move on to my second topic, but in the meantime, I will play a short ad. So I will be right back. Okay, I believe we're back. I was just reorganizing here because I don't really need the paint window at the moment. So the idea I had, and I'll probably want to get my. I'll just go from the from what I remember. So this is not something that I necessarily have any proof for whatsoever. It's just an idea I was tossing around in my head, and I have done a little bit of research into what other people have said on the matter. But this idea is so it's the idea that so in three-dimensional space we have momentum. So what that means is that if if I'm moving and I have mass, then I have some vector associated with that, which tells the direction and the magnitude of that of my momentum in that direction. And what momentum does is when I collide with something, then I transfer momentum, and there's always this conservation of momentum, which plays out into so it the conservation of momentum means that you can't create or destroy momentum. So in a collision, the momentum is always preserved. So either I kept it or I gave it away or somewhere in between. So what I was considering is that the idea of considering time as a fourth dimensional space dimension. So now this is not a new idea. So time, whenever people are talking about space time, then they are talking about time as a fourth dimension. And so whenever people consider trying to visualize a fourth dimensional a system, it's nice to think of time as a fourth dimension, because you can think of it as a spatial dimension. Because if you think about where we are in time, and actually the program just replaced, and so it didn't kick in the optimizer, which is a little disappointing, but it just means that the program is learning, so that's not a problem. So if you think about time, and so where we are in time right now, you can be somewhere with the exact X, Y, and Z coordinates in this moment in time that someone else was in a different moment of time. So it's almost as if there's another axis for where it locating something, and for identifying it. So you can set, so it'd be like an X, Y, Z, and then I don't know, a T, but probably not T, in terms of a coordinate. And so what I was considering was the idea of there being momentum through time, because obviously we're moving through time in what seems to be a constant rate. So at least our experience of time is constant. And so when we consider time, we it could the idea isn't too crazy to think of there being a vector with our momentum and there being a slight lift into the time axis, because that means that we are moving forward in time, or at least what we consider forward. So what is interesting is when you consider a sort of time component to this momentum, then you can start to visualize the effects of large forces, and why time is dilated in those forces. So what happens is, and so this is all stuff this is all ideas that I've speculated and then went and tried to research. This is not necessarily me saying exactly what's happening. This is just what I was tossing around. So what I was considering was the idea that since gravity is a radial force, and it creates a field in all directions, that it would also create a field in in the time direction. And so what that would mean is that if you had a force in the time direction, then it could actually change that vector to be moving faster or slower through time. And so what happens is when you have a inward force, you get a arc, and with that arc, there is a acceleration, but it is a orthogonal acceleration, or at least part of the component is orthogonal. The normal acceleration is orthogonal. So that acceleration changes the direction of a vector. And if we're talking about this four-dimensional space-time in terms of a coordinate system, then actually it may be easier just to consider 3 dimensions and just consider our space 2-dimensional. So if we just think of a flat surface with an x and y, then time can be the vertical axis, but that still doesn't necessarily allow you to visualize it as much. But so what I was saying is that if you have a vector moving through this field, then it could pull that vector, it could shift the direction of that vector, so of that velocity, so that it is moving at a different rate through time. And the interesting idea is that in terms of large gravitational fields, and even our gravitational field for that matter, is that we see a time dilation through that field. So, and so this is all based off of this whole concept is basically around the ideas that were put out by Einstein and later touched upon by other physicists. But what is interesting is that it kind of coincides with this idea of there being this total momentum through time and through time and space. So what I got, and I may be completely wrong, so I challenge you to correct me in the comments and whatnot if I am wrong. What I was getting was that we have a constant velocity necessarily through time, through time space, and so when we hit something that changes the direction of that, the magnitude of our velocity doesn't change, but the direction of it does into this fourth dimensional idea of a time axis. And so that's what was intriguing to me, was that large forces can actually alter the object's experience of time. And so we have seen that with particles that are decaying, that would normally have decayed in a short amount of time. If they're moving really fast, then that's not necessarily a large force, but I also had some ideas on that. But so it's the idea of time dilation in a large field. So this isn't restricted just to gravitational fields. It also applies to large electrostatic fields. And so there is a time dilation that could be associated with an object being in a large electrostatic field. And that got me thinking that if one could create a capacitor that could create such an intense field of electrostatic force, then then you could induce a time dilation in an object, for instance, and then so the side of it that I didn't necessarily get an answer for, and what I was considering, was that when you induce a time dilation, it's a change in momentum. So if even if there is some resistance to that, to going a different pace through time, or to going a different magnitude of the time component, for that vector, if there's some resistance that forces it back to what we consider normal at the moment, then it I in my eyes it wouldn't be instantaneous. So that may be completely wrong, and I'm not completely sure about that. But in terms of normal momentum, so let's say we have an object flying through the air, then it will go. It will stay at that speed until the air slows it down. And so what I was considering was the idea that if something is moving faster through time and something else were to collide with it, or at least try to occupy the same space as it, then it could technically collide in the time axis with that object and push it and dilate its experience of time. So that was the idea that I was tossing around, because that would basically be time travel, but it wouldn't necessarily be practical, because you'd be being hit by this massive force to knock you forward. Um, so and that would require also a immense amount of power to create that such a field in a capacitor. Um, Either that, or you would have to uh, make the particle that you were working on extremely small so that it could fit in a extremely tight capacitor that would create a larger field. Um, but so that was the idea, and if you have any answers or comments on that, I would be very open to hearing them, because I wanted to I just wanted to get get my head around the idea of whether or not something could necessarily be whether a particle that is being that is having its time dilated could technically collide and transfer that momentum in the time axis to another particle. So I know that's quite a mouthful. Like I said, this is all uh, late night, kind of just staring at a notebook paper and writing everything I was thinking down deal. So I understand if this wasn't necessarily what you were looking for when you turned on the video, but um, this was just something I had in my head, so I wanted to get it out. I wrote it down, and then what actually happened was I wrote down everything I was thinking, and then I researched and found out that most of what I was thinking was already something that was a basis in upper level physics classes, and the rest of it was wrong. um, so uh, the idea of there being a momentum is true, and we see that with particles moving through space and whatnot at high speeds, because they are affected by these relativistic effects. And I talked about relativity in a previous video. Um, so the equations that you use to calculate that do encompass time as a factor. But my idea, and it may be a little science fictiony, was the idea to induce that so that you could technically force something forward in time without the field itself. But then at that point, you might as well just force it through time with the field. So I'm not really sure about that. But um, that was just the idea I was tossing around. Um, so I wanted to let you guys know about that, or at least get it get it off my chest. But other than that, I don't really have too much more to talk about on the topic. I'll check to see if there are any comments. Um, and so I believe I will move on to my next section, which is the normal section where I draw something on paint based off of random numbers. So I will be right back. Okay, I believe we're back. So I will be working on the section that I normally do with my paper here. So I'll generate 3 random numbers. The first one is 12, which is a forklift. The second number is 25, which is twinkle. And the third number is 18, which is leathery. We're having some interesting ones in these past few uh, sections. So let's just start with the basis. We'll get the forklift going. So we'll get our forklift, and so it's going to have the little wheels in the front, and then the cab, and trying to get a good mental picture of a forklift. Okay, so I know that it has larger tires in the back, just in terms of weight compensation. That is not an eyeball, by the way. So I will go ahead. Actually, I can probably color these in. Get some gray. Okay, and then we know that they have the arms, so we get this lift, and then so this is the basic idea of a forklift. We have now this is a two-dimensional drawing. That is not what I wanted. So obviously we are not seeing the fork aspect, but I would like you to imagine that there is another side to this fork over on the other side, assuming that we have a third axis going through the screen. So I can probably color this, the rest of this here with my yellow, just color it in for good measure, so bam. And we'll get this going. Okay, so we have our forklift, and so our other words, I'm starting to get a little lost for what I want to work these in with, but I will just go with the basis for now. So possibly we'll just throw some ideas out. Possibly the forklift could be lifting something that is leathery and twinkly. So I'm not sure what necessarily would be both leathery and twinkling, but then perhaps some studded chaps. So we can have a let's go with that. So we'll grab our brown here, and we're gonna get a cardboard box to start out, and it's going to have our opening and like that, and then I will color some stuff in here. So we have this cardboard box, and it's got It's got our before mentioned chaps in them. There are a large quantity of chaps in here, and so we have uh, this whole supply of leather goodness, and obviously we have to touch these up because they are quite the fashion statement. They need to be done justice. I'm just gonna make this more paint friendly. Okay, so we have this box of chaps, and we can write chaps on it. And obviously, if this is the payload, the driver will probably be someone who is interested in them. Oh, we can't forget about the sparkles. So these are twinkly, and they are projecting light outwards off of their reflective bedazzled surfaces. Um, just like any good pair of chaps would. So then we will need to have our driver here. So obviously if he's driving, we need some mechanisms here. And then we'll get some handles there. And we'll start the process of drawing the driver. So this is nothing like the Environment Project driver. This driver will have less computers and also less clothes, I would imagine. So we'll have our normal biker jacket man, sleeveless. That's going to be a little close to the roof for his comfort, so we'll start over. And we'll get the jacket going, and then this is going to be his arm, and that is a interesting arm, but I'm sure the ladies love it. That's all that matters. And we'll give him a black leather hat, and also we're going to color this in once we get the chance, but at the moment I'm not doing that. Okay, so obviously he's bringing these chaps to some sort of leather convention, and the sheer quantity of the chaps required that he needed a forklift, just because obviously forklifts can lift a little bit more than the average human. I did not know. I don't know if you knew that, but this is a common knowledge idea. Nope, I still didn't fix that, did I? So if we have this man driving this forklift forward, then he will have a momentum, and this momentum can be represented by a vector whenever I get around to drawing the vector and stop adding more aspects to this picture. So this vector can be represented anywhere in space because vectors are not dependent on their origin. So let's say that this is his momentum, and obviously it is a large momentum because the forklift itself weighs a lot, and actually it has a lot of mass, sorry, and the box of chaps, obviously if it is needed, if a forklift is needed to lift this box, then it must be relatively massive itself. So we will assume that he has this momentum mv, which m is the sum of the mass of the forklift plus, that's not a K, that's an F, plus the mass of the chaps, and also any other mass that's included, perhaps the mass of the driver, we can do that. And this velocity will all be the same due to the fact that they are all one body at the moment. But I'm sure that the chaps will be connected to many other bodies later. Hopefully they will be on, and we can leave the mental picture at that. But also, he will be moving forward through time, which we can consider in this direction if we so choose. This would assume that this is a two-dimensional space where the x-axis is in this direction, the y-axis is in this direction, and the time axis is in this direction. And we could imagine that maybe the z-axis is in this direction. But it's a little hard to conceptualize a fourth-dimensional coordinate system in a two-dimensional visualization. So that's why I was saying it would be easier to represent this idea by naming space as a two-dimensional plane and having time orthogonal to or normal to that plane. Now, time would be normal to all three of the axes, but this is hard to grasp in our normal sense of geometry, so I will not attempt to draw that any more complex and correctly. So I believe that we have a nice picture here, and I will leave the picture here, but I want to thank you guys for watching, and like I said, Wednesday I have big things to talk about in terms of the environment project, and I will be working a little bit on that as the days go in terms of this week. So I have a lot of changes, and I do think so. The current running of the environment project is in the environment project 1.3 in terms of what I've been labeling it. So this is the first version of it, but I have made some updates to it, as you have seen on the streams. And so I believe that this new update, because of the sheer overhaul that I need to do on the way that Jeffrey thinks, this will be environment 2.0, which I have deemed the mental assets update. In other news, the optimizer did not kick in this stream, and so part of me is tempted to stick around for the next 2 generations to see if it does, but I know that that this would be a significant amount of time. So I will leave it here, and we will pick back up where we've left off in the next stream. But I want to thank you for watching, and I will see you on Wednesday.